So today, actually, I would like to start with a question which Andrew asked yesterday, something about intensity, which actually makes I mean, the question made a lot of sense, because when we calculate average, which intensity is supposed to be, it's an average value of a magnitude of Poynting vector, right? So, however, what average to take? Well, one thing is that it was average with respect to time. However, how long time should we take? And if you remember, or you can actually check it on the on YouTube, that what I indicated is that those oscillations happen so fast that actually we don't care about it, that our eye is not able to react. However, we are able to react to something which happens in 1/20th of a second, which means that the average, which we take for average for an intensity, we have really consider average over a period of time for which our eye is unable to react, which means that actually it has to be average over a relatively short period of time. And I was thinking about it, how to make it kind of more precise. So definitely it will work if you consider just one oscillation of electric field. So if you calculate average over one oscillation of the fields, then this should be considered as the intensity. Yeah, because I mean, how much time is it going to take to perform one oscillation by a wave? Imagine that a sinusoidal wave travels, right? So in one period, it is going to travel one wavelength, right? Do you see that? Yeah, so if this is a wave and in one period it will just move by one wavelength. Well, how fast the wave is traveling? With speed of light, which means that we will have to divide one wavelength by the speed of light, and this will be the time of one oscillation at this location. So really, let's just to evaluate what kind of quantity we are going to get. Wavelength is about of the order of a micron, less than a micron, half a micron for visible light. So in one oscillation, wave is going to travel, let's say 1/10 of 1 micron for simplicity. Now, speed of light is 3 × 10⁸ meters per second. So it means that I have to divide 1 × 10⁻⁶ meters by 3 × 10⁸. So it is 6 and 8, so it's -14. It will 1/3 times 10⁻⁻14 of a second. And this would be a really good period of time to define intensity. Now, if the oscillations are actually not harmonic, which means that they are not exactly sinusoidal function, but let's say that the amplitude of that sinusoidal function decreases, then we would say that intensity is variable. And now if you think about, let's say, if I think about average intensity over a period of a day, then I have to take average value of average values. Do you see that? Do you understand me? Because intensity itself is already an average value of Poynting vector, and then average over the period of a day, I have to take average of those averages. So do not confuse now average over a whole day with the intensity of the light. We will have to distinguish these two things. So, for example, if a lamp is if we have a light bulb and we, even if we turn it off, you see that how it is becoming dimmer and dimmer and dimmer. So I could calculate, for example, how much energy falls on a particular surface from that lamp which is being turned off. And I can take function which describes intensity versus time. How about if I think about it? We think about it. So consider that when we turn off the lamp, that the is time, and here is intensity of time, and the intensity decreases exponentially with time. So we will have that intensity at an arbitrary instant t is equal intensity at the beginning, I mean initial intensity, and let's say that it is exponential function of time minus t over certain time constant. So if I consider now a surface, and for simplicity, let's say that the light is falling at normal incidence on that surface. Let's say that area of this surface is A, and that the intensity is uniform over this surface. So how much energy is going to fall on this surface in the process during the time when the lamp is being turned off? So this total energy will be integral from that. Oh, how about, well, so in a certain instant t, when intensity has this value, I have to multiply intensity by the area and by the time to get energy falling on that surface within time interval dt at instant t. Or so it is from t to t plus delta t. This is energy which falls in this time interval, t plus dt. All right, so now how about throughout the entire process, I will have to add over the entire interval. All right, now let's see what, so this will give me total energy falling on that surface. So what would be the reasonable variable for integration? Well, let's explicitly write down this function. So this is I0 e to negative t over tau times a times dt. What would be the reasonable value for integration? What is variable here? Let's say I0, is it variable or constant? Oscar. Constant. E, tau, t, variable. A, constant. And here we have t, right? So what variable would you choose? I mean, we don't have much choice now, right? Because we have only one variable. It really makes sense to take this variable as the variable of integration. So now we will have it from t0 when we, let's say, turn off the light bulb and to infinity. So actually we know how to integrate this function. I'm not going to do that. Yes, so we can take out constants and integrate the exponential function. Now there is I mean, so far I was talking, I mean, yesterday and today I was talking only about surfaces oriented in such a way that the light was falling at normal incidence. But what will happen if the surface is inclined? Yeah, so let's say that the normal makes such an angle. I mean, this is vector normal to the surface. I mean, to the direction of propagation. Perpendicular to the surface, normal to the surface. So let's say that now it makes angle theta with the pointing vector. So would I have to modify this expression in order to determine how much energy is falling on this surface? Would I have to change this equal sign? No. How about this one? Yes. I will have to change. I will have to change expression over here, because what is this A? This A requires a surface which is perpendicular to the propagation. Now, I can recognize that if I take a surface like this, do you have appropriate imagination to imagine it? Yeah, I took actually a surface. So from this side, if I watch from this side, I'll see this surface which is kind of perpendicular. And now I can recognize that whatever crosses this surface is going to fall on that one, on that inclined surface. So really, in order to find out how much energy is going to fall on this surface, I will have to figure out how much energy crosses this one. So this A now has to be area of this surface. All right. If this surface has area A, angle between, and an orientation is like that between a pointing vector and the normal vector to the surface. So what will be the area of this of this surface over here, which is now perpendicular to the propagation of light? If I because you can think about it that you are sitting, you are the source of the light. So your eyes are source of the eyes now, of the light. And let's say that if I point it this way to you, how big area you see, I mean, how big is this area through which you see the sheet of paper right now? Compare it to the area of the sheet of paper. I mean, yes, it's the same as the piece of paper. Now, how about now? Is it bigger, smaller, or the same? Obviously smaller. How much smaller? Cody, how about you? Yeah, because I mean, how much of the surface you see now? Not very much. All right. If I were able actually to keep it still and maintain it flat, if I align it in such a way that it will be perpendicular to the direction from Cody to that page, how much Cody would see? Nothing. Basically nothing. Right. Okay. Now how? I mean, go ahead and relate the direction from which, I mean, let's say that Cody glows. He does actually. We all glow. And this is actually how night vision goggles work, because well, we are a source of infrared light. I mean, if I don't forget, I will maybe even bring an instrument tomorrow so that we can measure how much energy this instrument is going to record from you. It happens that the hotter the object is, the more energy it emits, and well, the wall is cooler than I am. I am hotter than the wall. Therefore, I emit more energy than the wall. So if you have a device which is sensitive to the radiation which the wall and I send, and both I and the wall send infrared radiation, but I send more of it. Therefore, I glow more, and in night vision, with night vision goggles, you will see me as a brighter spot than the wall. All right, so have you figured out actually now how should I modify this? Instead of this, I will have to multiply it now by a certain trigonometric function. Which function? I mean, I know that probably when you see it in an arbitrary orientation, it is harder to see. How about if I look at an angle like this to this entire picture? Yes, so here we have projection of this surface. Now, how this edge shrinks when we incline the surface. In other words, compare this length with this length. It's constant. It's the same, right? Now, this one gets shorter, right? And actually, so I'm looking now from this direction and try to figure out by how much it gets shorter. And now we have angle theta here. I can recognize actually that this length is equal to this one, right? Can you see that? Which makes a right triangle like that, with angle theta here. Well, if angle theta is here, one of those is theta. Which one? This one. This one is also theta. Yeah, think about it. What will happen if I make it smaller and smaller? Right? If I make this smaller, so this angle also is going to get smaller and smaller. So these two angles are equal. Now I think you can recognize what is the length of this side. How big is this side? Well, it's this side multiplied by cosine of angle theta. So this side of triangle is not affected by inclining. This side is equal to this longer side multiplied by cosine theta. So now how do I get the area of this rectangle? I multiply the length of one side by the other side, right? Now over here, how do I calculate this area? I also multiply one side by the other side. These two are equal. Now this side is equal to this one times cosine theta. So that area is going to be A times cosine theta. Do you see that? So here I will have to multiply it by cosine theta. All right. Now let's see that we consider if we think about how much energy is absorbed by a roof of a house over the period of a day, which is actually now a quite important technological applications. You know that we have a problem with energy, so we are looking for various resources of energy, and one of those is sun energy. Actually, as I indicated in the quiz today, the intensity of light is 1 kilowatt per meter square. Now, think about actually what has. I mean, what is 1 kilowatt? How much power really it is? Something which you can feel. So think about items in your household, whatever. Try to figure out what will have a power of 1 kilowatt. A washing machine, right? Are you sure? Actually, you're right. A washing machine will consume a power of 1 kilowatt. So if we are able really to harvest light properly, now one meter is about this big. So if I collect light, sunlight, falling out to, well, area about this big. And if I were able to convert this sunlight energy to a useful energy, I could run a washing machine with that. How many light bulbs I can run with that? What kind of light bulbs are you using in your household, Andrew? About 100-watt light bulbs. So how many can I run with that? 10 light bulbs, right? So this is the energy. However, if we put, well, we are putting already, as a humanity, we are putting a lot of those devices. They don't have efficiency of 100, and if they have efficiency of 10, we are already we are already happy. However, when we put those panels on the roof of the house, well, there is something else. There is another factor which actually affects how much we harvest of that intensity falling on that panel. The problem is that the sun does not remain still, right? So at the sunrise, what power are we absorbing in sunrise? Almost nothing, yeah, because the sun is coming from a side. Maximum will be when the sun is just above the panel, and at the end of the day, it also is zero. So although how would we have to calculate? I mean, what would be variable in this expression over here if we were calculating energy falling, let's say, on a photovoltaic panel on the roof? Let's think about first intensity. Is intensity time dependent? Okay? Because, I mean, over here we were discussing a situation when we turned off the light bulb and the light bulb was getting dimmer and dimmer and dimmer. Now, if we think about not a light bulb by the sun, what should I put here? Is it variable or constant? Yes, Andrew?
It's nearly constant. We leave out the sunrise and sunset where it's more optical.
Very good, right? The sunlight, I mean, because actually the sun, even over our the span of our entire life, does not dim. So we can assume that intensity over a day is of the sunlight is constant, except for the fact that the sunlight has to go through the atmosphere. And if we look at the atmosphere, which is about 100 kilometers thick, so let's say that our house is here. So at the sunrise, the line has to travel to this thickness of air. At noon, it has to travel through this thickness of air. At sunset, it has to travel again through this thickness of air. So at noon, the intensity over here is going to be higher than that at sunrise and sunset. However, even if I think about 1 hour later, I can really assume that the air, fortunately, is pretty transparent, provided that we don't have another phenomenon which happens in air. What am I talking about? Clouds, right? So clouds actually will make it variable too. But let's say that we have a sunny day. We can assume actually that this is almost constant throughout the course of the day. How about other factors? Angle is going to be a function of time, correct? So now this is going to be a function of time. And let's say that we pick such a situation that the roof is inclined in such a way that the sun, that there is a moment that at midnight, that at noon, for example, the sun rays are falling at a normal incidence to the roof. So what are the values? Well, how actually this angle changes and what are the possible values for that angle. Because now we have two variables here, right? One is t. It happens that that function becomes constant actually, so we don't have this dependence on time. But here we have one constant, which is angle, and here we have one variable, which is the angle, and here we have another variable, which is time. And actually, it doesn't matter which we choose for the variable of integration. However, we should choose only one, either angle and then express time in terms of the angle, or we could choose time and then we have to express angle in terms of time. How about if we express angle in terms of time? Explicitly, how this angle depends on time. Well, what affects it? How the angle depends on time. Yes, Oscar. Yeah, I see that you know it. Right. Okay. So we will have to figure out at what time it rises and sets. However, if I consider this situation that the sun goes there is an instant that the sun rays are normal to the roof, then what would be the smallest and the highest angle? From 0 to 100. Well, I mean, depends. Consistently with this one, it shouldn't be from 0 to 180. Yeah. Because I mean, be careful when you never change the meaning of the variable. If I pick that angle to be the angle between the normal to the surface and the rays, then now we have to do it also. So at noon, the angle will be 0. Correct? The angle will be 0. This angle. Now at sunrise, minus 90. I buy that, and the sunset it will be 90. You can reverse it too. You can say that at sunrise was 90 and minus 90 at sunset, but you have to be consistent. Now, how it depends on time at any instant? Well, what actually makes that angle variable? What fact about universe makes the angle variable? Rotation of the Earth, right? Unfortunately, Earth rotates at a constant rate. I mean, not true, but over our lifetime it does. Over our lifetime, the rate at which rotation will drop is I think, oh no, this is about 200ths of a second per century. Oh, so it will get slower. I mean, after you die, it will be probably turning. I mean, the full day will be by 100th of a second longer than it is today. All right. Yeah. So over here, I will have to put rate at which Earth rotates multiplied by time. I would have to put it there. Okay. Now I promised also yesterday that I will show you how I mean the effect of interference. So I'll show it on a mechanical model. So here is a mechanical model of a wave. I can, did you see that wave traveling? I mean, until it got bounced from that other side. Now what I want you to look at is this point. What happens at this point as two waves travel through this region? So I will now make two waves from both sides, and I will make them in such a way that crest is going to meet with crest. So I simultaneously move them up. Did you see how far this point moved compared to these two? twice as high. All right, now I'll try to do something else. I'll make this one up and this one down, and also observe what happens here. Did you see it? This point. What did this point do? Didn't move, right? So there were two waves. However, crest of this wave was meeting trough of this wave, and they well, cancel each other out. So actually this point did not perform any oscillation at all. I can actually even make a, fact that, look, that if a wave travels and gets to the end, it is going to be bounced back. You see that? So it's going back and forth now. I will actually take this take advantage of it, and I will just send wave one way, and then allow it to interfere with the wave which is reflected back. Yeah. So now this is effect of interference of the wave which I'm sending and the wave which is reflected. And as you can see, there are places like over here where the wave, in the result of the interference, actually we practically have no oscillations, also over here. However, at this point and at this point, we have higher oscillations than the ones which I'm sending. So in the places where they cancel each other out, we say that they interfere destructively. And so here we have destructive interference. We had destructive interference, and the regions where they reinforce themselves, we say that we have constructive interference. All right. Now, how about if I go to the discussion, and I think that I will not. I'll show the demonstration tomorrow, relevant to this. What I was. Well, maybe I will have time. Actually, I see that I did not turn on the projector, so I will turn on projector maybe, and first I show you the effect. Okay, good. Now I will do now the same trick with light. I will make light to interfere, light waves to interfere. So take this away. And let's see what I... And I will have I'll put two slits So here I have a source of light, and there are two slits over here. So light is passing through two slits. I'm not sure if you can see it well, so how about if I turn off the light? Now, can you see a pattern over here? There are bright and dim regions, and actually what you observe over here is a combination of two effects. One is interference caused by a single slit, and the other one is result from double slit. Maybe I will first put a single slit. Yes, a single slit causes interference, and we have, well, at the middle we have we have constructive interference, then we have a region of destructive interference, constructive, and so on. Actually, one can precisely derive the formula for the distribution of those intensities. Now let me see. I can put different patterns. Here's this. What is this? Oh, it was still single. Oh, how about I'll pick now a case in which I can vary the thickness of the slit. So depending on this, how narrow is the slit. Right now I'm getting that slit narrower and narrower. This is very narrow slit. Now when the slit gets thicker, the pattern gets shrunk. Now I saw that over here somewhere I have also an aperture. So this is of a hole of a particular shape. It's probably a rectangle. And this is a hexagon. I mean, the light passing by through a hexagonal opening. This is a pattern which is for a round hole, small hole. So you can see, well, we have a bright spot at the center, which means that we have constructive interference there, and then we have destructive interference and concentric. We have concentric rings as the result of interference. This is also a round hole, but of a different diameter. So depending on the diameter, I can make this pattern, I mean the pattern more or less stretched. Okay. So I think that actually it will be the right point to, I don't want now to start theoretical background on it because I will not be able to finish it by the end of the lecture. So we will come back tomorrow to explain what we saw today. And on the way